All right, so in this video, we are going to be taking a look at using familiar power series to write uh, power series of similar looking functions. So what we have here is we recall that the power series for 1 over 1 minus x is the sum from n equals 0, x to the n. We should note that because of some displaying error, that 1 over 1 minus x is the same thing as negative 1 over x minus 1 if we sort of factor out the negative 1, but I'm going to try to not write it that way because I don't like it as much. So the first part of this asks us to find the power series for 1 over what is essentially 1 minus 3x to the fifth. All right. Now, we should note that the 3x to the fifth here plays the same role as the x here, right? I'm simply evaluating this function. If this were f of x, I'm simply evaluating f at 3x to the fifth. So if I do so, then that is f of 3x to the fifth, which then is in turn necessarily the sum from n equals 0 to infinity 3x to the fifth to the n, which is a reasonable way to write something. But to give it more the form of a power series, we could also say that that is the sum from n equals 0 to infinity 3 to the n x to the 5 to the n, which we could further massage into 3 to the n x to the 5n. And that would give you a power series representation. The second part of the problem asks us to find a power series representation for x over 1 minus x, which we may notice is x times f of x, which necessarily then is x times n equals 0 to infinity x to the n. Now that may be well and good, but if you wanted to sort of give this a formal power series expression, we note that there is n x's here, there's another x here, and that gives us x to the n plus 1. All right. And finally, we want to find a power series for f, for capital F, which is an antiderivative of f such that f of 0 is equal to 1. So we first note that the antiderivative of f of x in general is, which is capital F in this case, is an integral of the sum x to the n from n equals 0 to infinity with respect to x. This in turn is the sum from n equals 0 to infinity x to the n dx, which in turn is c plus the sum n equals 0 to infinity 1 over n plus 1 x to the n plus 1. Now, I'm not necessarily a fan of starting this out having an n plus 1 term in the numerator like that. You can leave it like this if you're fine with it. The other thing you could do is rewrite that, and then we note that the smallest power of x when n is 0 is 1. So we could rewrite this series if we chose as a sum n equals 1 to infinity x to the n 1 over n. Again, these need to be the same, just like these were the same. The smallest term was 1, the smallest term will be 1. So these two expressions are equal. Now, from here, I know that I'm looking for a specific c such that when I evaluate 0 for f, that's equal to 1, and that this all has to be equal to 1. So we should note that since f of 0 on the one hand is 1, on the other hand it's c plus the sum n equals 1 through infinity of 1 over n, 0 to the n, which is c plus 0, we have that c is 1 and f of x is 1 plus the sum n equals 1 to infinity 1 over nx to the n. All right, thank you very much. I'll see you in the next video.